There is a fault line sitting just off the western coast of North America that has not produced a major earthquake in 326 years. And this year, three separate research teams published findings that all point in the same direction. The fault is shallower than we thought. The shaking will be worse than the models predicted, and the two most dangerous fault systems on the West Coast may be capable of triggering each other within minutes. That last part is new, and it changes the worst-case scenario in a way that most people have not caught up to yet. For decades, the standard nightmare was a single massive earthquake along the Cascadia subduction zone, a magnitude 9 event shaking the ground from Northern California through Oregon and Washington for 3 to 6 minutes. That alone would be catastrophic. But research published in 2025 and presented at the 2026 Seismological Society of America annual meeting now suggests that the Cascadia subduction zone and the San Andreas fault, two systems scientists had long treated as independent, may actually be synchronized, meaning a rupture on one could trigger a rupture on the other within minutes to hours. Not one megaquake, two, potentially hitting San Francisco, Portland, Seattle, and Vancouver in a compressed time frame that no emergency response system on Earth is designed to handle. By the time we are done here, you will understand exactly what the new research found, why it overturns three fundamental assumptions that hazard planning in the Pacific Northwest was built on, and what it means for the roughly 15 million people living in the path of what scientists now believe could be the most complex seismic disaster in American history. Let me start with the single most important revision. For decades, every hazard model for the Cascadia subduction zone was built on a specific assumption about the depth of the Juan de Fuca plate as it dives beneath the North American continent. That depth matters enormously because the closer the fault interface sits to the surface, the less distance seismic energy has to travel before it reaches the ground that people live on. Less distance means less attenuation. Less attenuation means stronger shaking. In April of 2026, a team led by USCI's seismologist Aaron Worth presented data at the Seismological Society of America annual meeting that fundamentally revised that depth estimate. Using updated offshore seismic imaging and a deployment of 192 temporary seismometers across a corridor from Tillamook to Portland, the researchers determined that the slab interface is sitting approximately 5 kilometers shallower than previous models had assumed. 5 kilometers. That does not sound like much until you hear what it translates to at the surface. According to Worth, this geometric correction alone increases the estimated peak ground acceleration from a Cascadia megathrust earthquake by 9 to 17% along the coast of northern Oregon. That is not a marginal adjustment. Building codes, bridge designs, hospital retrofits, dam assessments, every piece of critical infrastructure across the Pacific Northwest was calibrated to the older model. A 9 to 17% increase in projected shaking intensity means that structures previously considered adequate may not be. The same study uncovered a second finding that compounds the first. Beneath the coastal town of Tillamook, Oregon, the researchers identified a previously unmapped sedimentary basin. Sedimentary basins are geologically significant for one specific reason. They amplify seismic waves. When ground motion enters a basin filled with soft, unconsolidated sediment, those waves slow down and their amplitude grows. The phenomenon is called basin amplification, and it is well documented in earthquake science. The 1985 Mexico City earthquake is one of the most studied examples, where a lakebed basin amplified distant seismic waves and caused catastrophic structural failures in a city that sat far from the rupture itself. The basin beneath Tillamook was not in any previous hazard model. It was hidden. The communities built above it were designed without basin amplification in mind because no one knew it was there. Now, let me walk you through the second piece of research that arrived alongside these findings, because this is the part that changes the shape of the entire threat. A team led by marine geologist Chris Goldfinger at Oregon State University published a study in the journal Geosphere after analyzing deep-sea sediment cores representing 3,100 years of geological history. What they found was evidence of synchronization between the Cascadia subduction zone and the northern San Andreas Fault. Synchronization means that earthquakes on one fault appear to trigger earthquakes on the other. The team identified at least 8 major earthquakes on the San Andreas Fault that occurred within decades of large Cascadia earthquakes over the past 3,000 years. And in 3 specific instances within the past 1,500 years, including the most recent event in 1700, the data suggests the ruptures occurred within minutes to hours of each other. Think about what that means in practical terms. Goldfinger himself said it directly. An earthquake on one of the faults alone would draw down the resources of the whole country to respond to it. And if they both went off together, then you have potentially San Francisco, Portland, Seattle, and Vancouver, all in an emergency situation in a compressed time frame. The standard emergency planning assumption has always been that Cascadia is one event. You respond to it, you send national resources to the Pacific Northwest, you mobilize FEMA from across the country. But if the San Andreas fires within hours of a Cascadia rupture, there is no reserve. The resources that would have been sent north are now needed in the San Francisco Bay Area simultaneously. The mutual aid system that American disaster response depends on is designed for one major event at a time. A synchronized double rupture breaks that system entirely. Now connect that to the third piece of the puzzle, because this is where the picture gets genuinely complicated. A separate study from the University of Washington, published in Science Advances in February 2026, used 13 years of continuous offshore seismic monitoring data to examine how the fault itself behaves along its length. What researchers found is that the Cascadia subduction zone is not a uniform structure. The northern segment remains fully locked, silently building strain exactly the way the textbooks describe. But the central segment appears to be only partially locked, with evidence of slow slip events and fluid movement along perpendicular faults that may be quietly releasing pressure in some areas. The lead researcher noted that these fluid pathways could influence how an earthquake propagates along the fault, potentially limiting or redirecting the rupture in ways that previous models did not account for. This finding requires careful interpretation. A partially locked segment does not mean a less dangerous one. It means the system is more complex than the hazard models assumed. It could mean that strain is being released gradually through slow slip. It could also mean the segment will behave unpredictably during a full margin rupture. The honest scientific position is that partial locking introduces uncertainty rather than safety. Now, here is where some people watching this will want to jump ahead and ask the question that always comes up when Cascadia is discussed. When is it going to happen? The answer is that no one can tell you. What scientists can tell you is where we sit relative to the historical pattern. The Cascadia subduction zone has produced more than 40 major earthquakes in the past 10,000 years. The intervals between them cluster around 200 to 500 years. The last full margin rupture occurred at approximately 9 in the evening on January 26, 1700, 326 years ago. We know the exact date because Japanese historians recorded a tsunami striking their coast that night with no earthquake anyone in Japan could feel. They called it an orphan tsunami, a wave with no parent. Centuries later, scientists calculated the travel time for a wave to cross the Pacific and worked backward to the Cascadia Fault. On the American side, ghost forests still standing in tidal marshes along the Pacific Northwest coast, trees killed when the land suddenly dropped and their roots drowned in salt water, were dated to the winter of 1699 into 1700. Two continents, one story. With 326 years elapsed, Cascadia is deeper into its cycle than 75% of all documented quiet periods in the paleoseismic record. Current probability estimates put the odds of a magnitude 8 or greater earthquake in the next 50 years at roughly 37%, and a full margin magnitude 9 event at between 10 and 15%. 1 in 3 is not a remote possibility. It is a serious near-term risk. And the structures, the bridges, the fuel tanks, the hospitals sitting across the Pacific Northwest were designed to survive a version of this earthquake that the 2026 research now says was underestimated. Every time this fault is discussed publicly, the same predictable wave of claims appears online. The government is hiding an imminent mega-earthquake. Military installations are secretly being evacuated. Solar storms or planetary alignments are about to trigger the rupture. None of these claims have scientific support. The geological process loading the Cascadia Fault is the slow, steady convergence of two tectonic plates moving at roughly 4 centimeters per year. Nothing on the surface of the Earth controls or accelerates that process. What the new research has genuinely shown is sobering enough without any embellishment. The fault is shallower than we modeled. The ground beneath specific communities will shake harder than we predicted. A hidden basin will amplify that shaking in a town that was not designed for it. And two fault systems that were treated as independent for decades now appear capable of firing together. That is the real update, drawn from peer-reviewed science, presented at major conferences and published in leading journals. It does not require conspiracy theories to be frightening. It is frightening because it is documented. The most important practical message is this: Oregon's official guidance now tells residents to prepare for 2 weeks of genuine self-sufficiency after a Cascadia event. Not 72 hours, 2 weeks. Water storage, food that does not require refrigeration, medications for chronic conditions, battery-powered communication, and a relationship with your neighbors, because in a region that could be without power for 6 to 12 months, the first responders who reach you will be the people on your own street. The tanks at Portland's critical energy infrastructure hub, a 6-mile corridor along the Willamette River that stores over 90% of Oregon's liquid fuel supply on liquefiable soil, can be retrofitted to survive this shaking. Most of them have not been. The bridges can be redesigned. Most of them have not been. The hazard models can be updated to reflect a shallower slab and a hidden basin. That process has only just begun. The Cascadia Fault does not know about any of this. It does not know about the fuel tanks on the riverbank, or the sedimentary basin beneath Tillamook, or the bridges built before anyone understood what this fault could do. It only knows the pressure between two plates. And the pressure, after 326 years of silence, is still building.